I want you guys to recall this. If we have a charge moving in a magnetic field, say at a particular angle, we'll take this case. What happens? They will go in this manner. Remember? Now say we have bunch of them, not just one of them, bunch of them moving perpendicular to the magnetic field. What happens? What do you think happens? Everyone will go in that manner itself. Say there's one more charge over here. That too will follow a similar pattern, right? Does it make sense? So that's what we are looking at here, right? We have given a special name called as eddy current to talk about this phenomena. So basically what we're looking at is when a metallic plate moves through a magnetic field, electrons inside the plate experiences a force. That makes sense? This force causes the electron to move in a circular path. We already know that. And that is your eddy current. That's it. Right? We are just borrowing the concept from the previous set of topics. So I hope you guys remember that. So here we have it going circular. What direction? That is something that we'll discuss. For now, you guys know that this is your, as and when it moves in, it will gain some strength. Okay, not exactly, but gain some current in it, right? Some work is done, so that work is converted to this. So the name comes from the fact that it looks like, the pattern looks like a whirlpool, something like this. We just saw that now in the previous, I'm not able to draw, guys. Something like that. And so the name eddy current. Okay, so this is going to be useful for quite a few places. So we are studying this. What is the principle used in studying this or understanding this? Obviously, Faraday and lenses. Now, let's look at the definition. Eddy current are the currents induced in solid metallic masses when the magnetic flux through them changes. Right? So we know this is the same stuff everywhere. Now the directional aspect. So according to lenses, what does it tell? It has to oppose whatever is trying to happen to it. It has to oppose the change. If there's no magnetic field, it doesn't want magnetic field. If there is already magnetic field, it doesn't want to increase or decrease. Okay, so let's look at it practically. So what is that we are looking at? We have a plate attached to something that can swing. So this is say case A and case B. It's the same plate moving in this direction, say to the right. That's the direction of motion. And we have the magnetic field line going in. So basically, if you kind of watch it from a different angle, it might look like this. So we have the magnetic field going away. So this will be south, right? No, this will be north and this is south. So we have it going inward and to the right. So here it is, my bad. In case A, it is going inward. Means what? It is moving from case A, it's moving from no field to some field. So what happens? It should oppose that, right? How will it oppose? By making itself north over here and south at the other end. So to resist, what will it do? It will try to push. It will try to push. So how can some magnet push another magnet? By getting the same magnetic pole. So by getting same pole, right? So basically this has to become north because the other end is south. So how does a north look like over here? So this is north, by the way. And this is inward. So we are looking at south. The magnet what we're looking at, this end is south, and the plate here from our end should be north. So as per our right hand rule for getting a north, that is, it has to come out, right? So magnetic field line is going in is south, that's correct. It's going away from us, right? So this end is north. For getting north, it has to go in, what is this? Clockwise, right? Let me draw it off. Again, you always do it and then discuss. It should be something like this. This is for case A actually. Let me draw it that side only. This is for case A. So we want north, right? This end. So it has to be anti-clockwise. And over here, case B. Case B, just the opposite. Here, we are moving towards snow field. Moving towards less field. So it will try to oppose that. So it will create, so it will attract because it doesn't want to change that. How will it attract? By making this as south. So obviously it has to be other way around. So this is how we can figure out the direction. It depends on which point of time we are looking at. If it's going in, then it will try to oppose. If it's going out, again it will try to oppose, just that by attracting, that is by different poles. So how will it something attract north? By making itself south. Does it make sense? So this is the complicated part over here. If not, if you find that easy, then conceptually you guys know that. We have dealt in detail that a charge moving in a field will rotate, will take a circular path. Right? We have seen that in detail. So the next version of that is we have a bunch of charges in a plate or in a conducting mass passing through electrical field. So what happens with that? They will resist the change, and so eddy current is created and so on and so forth. So you just have to know what is eddy current definition and the principle and the directional aspect.